Alright, so at this point, we've looked at all of the possible combinations and we've generated 8 molecular orbitals out of the 8 atomic orbitals. There's one more step, and that's simply filling in the electrons. We started with 14 electrons, and so we fill 14 electrons in the MOs. When you're filling electrons, you should keep in mind both Hund's rule and the Aufbau principle, which dictate how you should fill electrons in orbitals of any kind. You want to start as low as possible and put electrons of opposite spin in each orbital. And as you go, when you hit a level that has more than one orbital on it at the same energy, you want to half fill each orbital at the same energy before you go back and start filling orbitals completely, because half-filled orbitals are more stable than filled and empty. So doing this, half filling, is a more stable situation than doing this. Than doing this, where I completely fill one and leave the other empty. It's much more stable for the molecule to have a half-filled orbital like that. And even though we have more electrons to add, it's good practice to fill orbitals this way as you go, even if you have more electrons to add. So right now we've only taken account of 8, so I'll go ahead and fill those in. Now we've taken account of 12, and finally filling in the pi star. Excuse me, we'd only taken care of 10 at that point. And filling in the pi star now, we've taken care of the 14. So what you should notice here is that the situation is quite a bit more complicated than simply 3 lone pairs and 1 sigma bond. What we actually have is 2 sigma bonds, a sigma s and a sigma p. But because the sigma s antibonding orbitals fill 2, those 2 orbitals cancel each other out. So there's a sigma bond canceled out by its sigma star partner, which is also filled. Similarly, we actually have 2 pi bonds, in a sense, corresponding to these 2 orbitals, but likewise, those 2 are canceled out by their filled antibonding counterparts, which means 0 bonding overall for the pi-type combinations. We see that the sigma star for the 2p combination is unfilled. As a result, the sigma bond essentially corresponds to that sigma 2p orbital right there. So what we might expect is that the sigma orbital or the sigma electrons in fluorine are more reactive than your typical pair of sigma electrons that might be formed from a combination of 2 2s orbitals. And indeed, that is experimentally observed. So building the MO diagram has told us some extra information that simply looking at the Lewis structure couldn't tell us. And this is an example of where molecular orbital theory really adds some real information to the conversation about organic molecules. Finally, I'll end today by talking a little bit about how we build the orbitals of complex organic molecules. So if you look at the molecule on the next slide, actually, what you'll see is that we have a lot of atoms here. Whoops. And to take each of these atoms and contribute 4 AOs and get out all of the molecular orbitals by considering combinations on every single atom would be a long and laborious process. The question is, can we simplify this process substantially? And luckily the answer is we can. Another difficulty with building up the orbitals of big organic molecules is, how do we go from 4 perpendicular orbitals, so the 3 perpendicular 2p orbitals and the 2s orbital, to something with a weird bond angle like the tetrahedral bond angle of methane, say, 109.5. It's unclear, at least at first glance, using, for instance, the principles we used with fluorine, how do we go from the 3 perpendicular orbitals and the 2s orbital to something with weird bond angles? And the answer is we use a mathematical construct called hybridization. So we take, for instance, if we need 4 atomic orbitals out, which we do in methane, to occupy the 4 positions of the tetrahedron, we take the 4 basic or simple atomic orbitals, as they're called, simple AOs here, we hybridize them. And what we get out is 4 orbitals in a tetrahedral geometry that we can then use in LCAO to form sigma and sigma star orbitals. Right? So hybridization is really the key to thinking about the molecular orbitals of larger organic molecules, and really molecular orbitals of compounds involving carbon can always be simplified using this concept of hybridization. So next time we'll look at how to identify the hybridization of an atom and really what that means both in spatial and energetic terms. What you can see from this is that spatially the hybrid orbitals are perfectly set up for the geometries that we actually observe of organic molecules. So for instance, because we took all 4 of the simple atomic orbitals, we call these 4, each of them is an sp3 hybrid. 1s and 3p's is where that notation comes from. If we only need 3 orbitals, for instance, to achieve a trigonal planar geometry, then we only need 2 p orbitals along with the s orbitals, so we call that sp2 hybridization. And finally, if we only need 2, well then we can just take 1p and 1s, and we call those hybrids sp hybrids. And we'll look at this in more detail next time, but that's just a little intro for you to the shapes of the hybrid atomic orbitals.